or we're continuing our reading of Individuation in the light of notions of form and information, part 1, chapter 3. I can't remember what section exactly we're on. The last bit that we saw had to do with the inductive and the deductive operations or modes of thinking, and each of them ends up in a form of transductive thinking, as Simondon describes it. Right, section 3, subsection 1, thanks. Yeah, so we have a transduction that comes at the end of a process of deduction in the wave theory of light. And then we have another transduction that comes at the end of a process of induction in the corpuscular theory of light. But then Simondon points out that there's still this gap between the two. We don't end up with the same results from the two sides, or there's a sort of incompatibility between the two sides, so that we still have to represent light as a wave in some circumstances and then as a particle in some other circumstances. And so what we're seeking now is some sort of overcoming of this gap between the two forms of transduction. So it would be like a second order transduction. He uses the term at one point, reflexive transduction, that will overcome this gap between the two different modes of thinking, or the two different representations of light. And so we're still discussing now, that's where we stopped last time, the relationship or what the theory of relativity brings to the notion of the individual, the physical individual, and how, because the mass of a particle, like an electron, can increase infinitely as the speed of that particle approaches the speed of light under the relativity theory. That means that the properties of that particle, of the corpuscle, are not inherent properties, but depend on the sort of life history, I guess you could say, of that particle, and its interactions with the rest of its environment and so on. So whereas the ancient atomistic theory and its descendants in various corpuscular theories try to represent the atom as, or the corpuscles, the individual particles, as being having a sort of eternal sameness to them. Like they don't have any inherent changes. The changes happen because of the combinations of particles, but the particles themselves remain the same. But under relativity, it's no longer possible to have that same representation of corpuscles as being eternally the same. So now we have to understand these seemingly inherent properties, like the mass of a particle, as being products of the history of those particles. And then we'll also, in a little bit, we'll get to what quantum mechanics brings to the notion of the physical individual and the modifications that we have to make to that notion because of quantum theory. But we're not quite there yet. So let's start. I think we're on page 132, if I'm not mistaken.
Yeah, I think we finished that long paragraph on 132.
This affirmation cannot be taken as a recourse to pragmatism. For the physical individual, when we say that relation is of the being, we do not take this as meaning that relation expresses the being, but that it constitutes the latter. Pragmatism is still too dualistic and substantialistic. It just wants to rely on the manifestations of activity as a criterion of the being. This is to suppose that there is a being distinct from operation, an interiority that the exteriorization of action authenticates and expresses by manifesting it. In pragmatism, action is the crossing of a limit. However, according to the doctrine that we are presenting here, this limit can neither conceal a reality nor be crossed by action, since it does not separate two domains, that of interiority and that of exteriority. This relativistic doctrine cannot lead to a subtler form of pragmatism like Poincaré's commodism, which ends up as a scientific nominalism. It is realist without being substantialistic and postulates that scientific knowledge is a relation to being. However, in a similar doctrine, relation has the status of being. But the realism of knowledge must not be conceived as a substantialization of the concept. Realism is the direction of this knowledge as relation. Here, with the theory of relativity, we see it go from the rational to the real. In other cases, it follows the inverse direction, and then what consecrates the vitality of the subject-object relation is the encounter and compatibility of these two epistemological directions. The realism of knowledge is the progressive growth of the density of the rapport that links the subject term and the object term. It can only be discovered if we seek out the meaning of this derivation. In inductive research, this is the first step toward the discovery of transductivity, through which the corpuscle receives a non-substantialistic definition of its individuality. Nevertheless, in the application of the theory of relativity to the electron, there remains an element that constitutes a substantial bond between the different successive moments when the mass of the electron varies, even if it always increases by tending toward infinity when the speed tends toward the speed of light in vacuum, i.e. the continuity between the different successive measures of mass and energy. Relation is not entirely on the same level as being when substantial magnitudes, mass and energy, are posited as capable of continuous variation. Here an important doctrinal point remains to be presented and specified before mentioning the epistemological characteristics of quantum theory. Quantum theory indeed supposes that energetic exchanges between wave and corpuscle or between corpuscle and corpuscle always take place in finite quantities, the multiples of an elementary quantity, i.e. the quantum, which is the smallest quantity of energy that can be exchanged. Thus, there is a lower limit to the quantity of energy that can be exchanged. But we should ask in what sense Lorentz's formula can be affected a priori by the introduction of a quantum theory, and how we should consider the possibility of the indefinite increase of a corpuscle's mass when its speed tends towards the limit of light, tends towards the speed of light. If we start from a very small initial speed that progressively increases at the beginning, we will see that when mass can be confused with mass at rest, the increase of kinetic energy equivalent to a quantum corresponds to a notable increase in speed. Thus, speed can be represented as increasing through abrupt leaps. Conversely, when speed is close to that of light, the increase of kinetic energy corresponding to the addition of a quantum translates into a minuscule increase of speed. When the speed tends toward the speed of light, the addition of a quantum of energy translates into an increase of speed that tends towards zero. The leaps of successive additions of quanta are increasingly minimal. The mode of variation of speed tends towards a continuous regime. So there's a few things to comment on in this bit. So the first has to do with this, when he talks about pragmatism here. I'm not 100% sure who he's thinking of exactly. I'm going to sort of guess that it might be William James, but I'm not sure. He criticizes what he calls pragmatism, or what he's representing as pragmatism, as being too dualistic because it's treating the manifestations of activity as a criterion of a being. So if we take something like the sort of pragmatist position that believing in something means something like representing its effects or for action or something like that. That's not a very precise formulation of the pragmatist position, but something along those lines. So there's a sort of representation of the consequences of that belief as being the important part, or as being the criterion for the belief. And so I think that's the type of argument that he's criticizing here. It's that representation of the consequences or the effect for action as being a criterion of the entity, rather than part of the entity's being itself, which is the position that he wants to maintain. So he criticizes along the same lines Poincaré's position, which is a kind of nominalism in the sense that I think what he's thinking of here is Poincaré presents a lot of the different sort of framework elements of a scientific theory as having to do primarily with commodity. I don't know how you'd say that in English. The usefulness, I guess, of different frameworks for physical theory. So it's physical theory is not about sort of understanding the real structure of the world, but rather of producing a representation that allows us to order our experiences in a useful way or something like that. And so Simondon criticizes that position as being something similar to the pragmatist one, and ending up in what he calls a scientific nominalism. So it doesn't allow us any, or it denies that scientific knowledge gives us knowledge of reality as it is in itself, I guess. So Simondon wants to have a scientific knowledge that does give us access to reality, but understood not as a set of substances, but rather as entities within a partially individuated field, so that there's always the pre-individual always remains, and individuated entities are only part of reality. So that, and then he introduces it, or he brings back in this notion that we've seen a couple times, that the subject-object relationship is a relation in the proper sense that he uses, in which he uses the term. So it's a relation that has an ontological status. It has the status of being. Knowledge, the subject's knowledge of the object is not just a sort of external rapport, an external putting into conjunction of a subject and an object that are sort of self-contained substances. It's rather that there's a process of individuation of the whole subject-object system, which and that's what the knowledge relationship is. And so that's the sort of goal that he's setting out for epistemology, so that we need to be able to represent the subject-object relationship as something that has the status of being. And then maybe one last point that I'll mention is so we sort of overlap a transition here in the text, because he's passing now to, so he's introduced a relativity theory, bringing about a modification of the notion of the physical individual, but then he's going to qualify that here and say that it's only, there's a limit to the to that modification. So because there's this continuity of the different degrees of mass and energy of a particle, that continuity means that the relation that we saw earlier, that how a relation is supposed to have the status of being, in this case, it doesn't fully have that status. He explains this a little bit further in the next paragraph, in relation to quantum theory and the theory of a quantum of action. And we'll see a little bit more on this later on, but this is the sort of central concept of quantum physics, is that there are discrete states of energy of a system, so that there are no possible intermediate states of that system. So, for example, the orbits of an electron, there are specific states that the electron can be in, and specific energy states in an atom that the electron can be in, and there are no intermediate states that are possible for the electron. So the electron sort of jumps from one state to another when there's a transition. And so the relationship of this to the relativity bit is that when you start from a very low speed of an electron, so an electron with low energy and where its mass is close to the rest mass, the addition of one quantum, so one sort of unit of energy, gives a significant increase in speed of the corpuscle. So it adds significantly to the energy of the system. Whereas when you approach the speed of light, so when an electron gets close to the speed of light, then the addition of one more quantum of energy gives only a very small addition to the speed of the particle. So as the speed of the particle approaches the speed of light, then the operation of that discontinuity, the discontinuity of action that is the core of the quantum theory, tends towards a continuum. So it never fully reaches a continuous level, but the closer the closer you go towards the speed of light, the closer you are to a continuum of action, as opposed to this discrete action that's characteristic of quantum theory. So that's why there's this this sort of remaining continuity, is sort of a holdover, I guess, or something that is not fully relational yet, because we don't have that, because we have that tendency towards the continuum. But we'll see more on this in the next little bit as well.
I'm not totally sure I understand why the fact that it approaches this, this continuous state means that there isn't a reality of relation, and why it would need to be discontinuous for that to be the case.
Yeah, it's not 100% clear to me either, but one point is that he's brought up with the crystal example and previous discussion of the of physical individuation. He's set out the thesis that a relation in the proper sense, so the relation that has the status of being, is always between a continuous term and a discontinuous term. So there has to be this heterogeneity, or this asymmetry between the two terms related, in order for there to be something like in order for there to be a relation in the proper sense. So when we end up, we don't have that discontinuous term when we approach the speed of light, or we tend towards losing the discontinuous term. So that's, I think, sort of what's going on there. I think maybe one point, a little bit of an aside, but because Alyosha mentioned that article, I haven't had a chance to read the whole thing, but I just looked quickly at the beginning of it, and it looks like what the article is doing is a little bit different than what Simondon does in the book, because what they're trying to do is to interpret the standard formalism of quantum mechanics in a sort of Simondonian framework, in terms of the pre-individual and so on. Whereas what Simondon is doing, as we'll see probably in the next couple of weeks, is working with the double solution theory, which reformulates the quantum formalism. It introduces a new term called the quantum potential, which doesn't exist in the standard quantum formalism. So Simondon was operating with a somewhat different quantum physics than is represented in that article, at least as far as I saw. So I'm not sure. Sorry, I'm not sure if the article really goes into the double solution theory at all, or if it sticks with the standard formalism. But that's something to keep in mind when reading the article, is that Simondon is operating with this non-standard theory. So the double formalism theory, double solution theory, is a non-standard version of quantum physics, which introduces this quantum potential, which doesn't exist in the standard formalism of quantum physics.
I was just going to say, I think you're right in the sense that the authors are kind of, that they have their own kind of pet theory, but I think the reason that the paper is helpful is more for kind of framing the philosophical premises, I guess, and like the presuppositions of ancient, then classical physics, like Newtonian physics, and then subsequently quantum mechanics. And I think what's interesting about it, even though, as you're saying, Simondon does have this like different interpretation that they kind of acknowledge, I think what was most helpful to me was sort of just explaining within the language of quantum mechanics, the notions of potentials as different than possibilities, and they have a particular sort of thing about the way that this, which I don't need to completely get into, but the way that an ancient kind of Aristotelian notion of possibilities was kind of imported wholesale into modern science, and how that kind of affected things. But I think it's interesting because it actually speaks to one of these paragraphs here, where on 133, where he says the realism of knowledge must not be conceived of as a substantiation of the concept. And he's going in this section when he's kind of, I think, I could be wrong, but I think he's kind of getting at the thing he's usually talking about with subject-object and the problem with this kind of epistemology, where you can end up with a version of quantum mechanics, which they even kind of critique a bit in the article, which is essentially about undecidability, I think the word is they use, or there's a way of looking at it that is essentially all about measurement, which obviously there's a truth to that, but it still kind of privileges the observer, and there's the importance for whether it's Simondon or I guess any approach to talking about potentials in this case is that there has to be a way of conceiving of incompatibility in potentials as inherent to the system and not something that's introduced solely in measurement. And I think it's a useful thought experiment because they kind of go through several different examples of how that problem was approached, and then they give one answer for how Simondon could potentially answer that. But I think it connects back to all the things we've been talking about. In individuation, there's all potentials are not exhausted, and there's even a need to maintain a way of notating and formulating the existence of unused and unspent potentials even after individuation happens. All that stuff is there. So I just want to speak up for reading the article. That's all.
Yeah, no, I'm certainly not saying don't read the article, but I just wanted to sort of give that warning that it's slightly different, or probably more than slightly. There's that difference. The physics behind what they're talking about is a bit different than the physics that Simondon was talking about, so they're working with more the more mainstream, the standard formalism of quantum mechanics, and whereas Simondon was working with the double solution theory of Rayleigh. So we'll see more on this in the next few weeks, but just sort of keep that in the back of your mind as you read that article. Okay, so I think we can go on to the next couple paragraphs. If someone else would like to read.
I can read. I'll just close out the section.
Sure, sounds good.
The importance of quantum discontinuities is therefore variable with the speed of the particle. Wait, hold on. Can you guys hear me? My fan is on. I don't know if that's too loud.
No, that's fine.
Okay. The importance of quantum discontinuity is therefore variable with the speed of the particle. This deductive result is important, for it shows that a particle, like an electron, tends toward a regime of continuity when its speed tends toward the speed of light. It is then functionally macroscopic. But it must be asked if this conclusion is fully valid. What is the veritable sense of this limit, i.e. the speed of light? What is absolutely important is not the exact measure of this speed, but instead the existence of a limit that cannot be attained. However, what would happen if an electron attained a speed very close to that of light? Would there not be a threshold beyond which the phenomenon's aspect would completely change? Physics has already presented at least a very important example of the existence of a limit that could not be predicted by simple extrapolation. We can trace the curves that represent the resistivities of metal according to temperature, and these curves are regular enough in an interval of several hundred degrees. Theory shows that close to absolute zero, the resistivity of metal should tend towards zero. However, experiments show that for certain bodies, instead of decreasing little by little, the resistivity abruptly falls below any measurable value. This is superconductivity. The phenomenon is produced for lead at 7.2 degrees Kelvin, at 3.8 degrees Kelvin for tin, and at 1.14 degrees Kelvin for aluminum, according to the experiments by Heike, Kamerling, Onus. Modern particle accelerators make it possible to launch electrons at speeds very close to the speed of light. This energy can then become quite considerable, as in Schenectady's betatron of 100 million electron volts, without the predictions that conform to the theory of relativity being disproven in any way. However, it can be supposed that there is a threshold not yet reached beyond which the phenomenon would change if we could reach it. Consequently, there is currently an empirical limit to the application of the electron's relativity. It is hard to conceive that this limit can be overcome because an infinite energy cannot be transmitted to an electron. Furthermore, there seems to be certain theoretical necessities for conceiving an upper limit to the characteristic physical parameters of the electron, like that of the electrical field that regulates the electron radius in classical representation. However, if we seek the temperature of a dark body whose density of radiation energy would be due to the propagation of this maximum field, then we find a temperature above the order of 10 to the 12th degrees Kelvin. This temperature is what seems to be at the center of certain white dwarf stars. Higher temperatures and more intense electromagnetic fields are not known. We cannot therefore found a reflexive approach around the possibility of the indefinite theoretical and absolute increase of the mass or energy of a particle like the electron, because for reflexive thought there always remains a distinction between a very broad empiricism and a universal empiricism. An infinite margin of the unexplored will forever remain between the very high levels of attained energies and that of an infinite energy. This is why it is difficult to speak about what an electron would be if it were approaching the speed of light in vacuum. It even seems difficult to specify if we should conceive the possibility of the existence of a superior threshold of speed beyond which the electron might no longer be considered an electron. This margin of imprecision in knowledge cannot be reduced by the adoption of quantum theory, since the increase of mass and energy makes the dynamic regime of the corpuscle tend toward the continuous, when its speed tends toward the speed of light. If there were a superior threshold of speed and energy, it could not be determined by quantum considerations. Here we encounter a domain of epistemological opacity that can cast its shadow on a reflexive theory of physical individuation and mark the existence of an epistemological boundary to transductivity. The agnostic consequence resulting from this would itself be relativized by the boundary marking the beginning of the domain of application, the structure of which could not be internally known. If it is itself a relation, this topology of transductivity can be transductible to another type of individuality.
So here we have a sort of empirical or a gap or a limit to empirical inquiry, in the sense that however high the energy that we're able to give to an electron or any other particle, so there's 100 million electron volts, and I'm sure the numbers are higher now with the Large Hadron Collider and all these other giant accelerators. However high an energy we reach, we're never going to be able to give an electron an infinite energy, which is what you would need to put an electron at the speed of light. And so it always remains possible, or conceivable at least, that there's some limit above what we've been able to reach, at which there will be this transformation of an electron into something different, or its behavior will be different than it is below that threshold. And so he introduced the superconductivity as an example of something like this threshold effect, so that as the temperature of these substances decreases, rather than having a continuous increase in conductivity, there's a certain threshold at which the conductivity increases dramatically, very, very abruptly, and so it's rather than having a continuous decrease, we have this threshold effect where it abruptly becomes much more conductive than it was at a slightly higher temperature. So it's always possible to think that in the case of the electron's energy and mass, there could be another threshold above whatever limit of energy that we've been able to reach with electrons. And then above that threshold, there would be some sort of transformation of the behavior of an electron, which is not accounted for in the relativistic theory. So we only have so there's no empirical way to close that gap. We have to sort of suppose, we have to leave that empirical inadequacy or that possibility open, but we want to sort of move beyond that inadequacy through transductive thinking, basically. So we will be able to take the notion of the individual that we developed through relativistic physics and use it to structure a different domain in a transductive way. So here, this is the reflexive transduction, or the second order transduction, where we need to apply transductive thinking to the results of a previous process of transductive thinking, because we run into a sort of limit of the one stream of transductive thinking that can never be overcome. And Angus has posted a couple of useful definitions and links in the chat related to superconductivity and some of the other notions that Simondo introduced in that last little bit. Aldrin, you should be able to unmute yourself. You're not server muted. Do you want to ask a question?
Cool. Yeah, just kind of, I guess it's a little bit at a distance from the specifics of the kind of the specifics, the scientific details. But you were saying a little bit earlier about the relation and the way the relation has a continuous and a discontinuous, I guess, side, and the relation is somehow I guess the way they're connected or they're related to one another. And I guess what I'm trying to understand is, so it seems like, okay, if I try to think what is the discontinuous, that's not so hard, right? It's an atom, or it's a sort of an individuated thing. Atomism does that kind of work, right? If I try to think, okay, what's something continuous? And that's kind of straightforward too. Okay, it's a wave, and you can go to, the wave style philosophy, and you can get that there. And it looks like what Simondon is getting at is thinking of this relation itself, right? Like the way these two are related or in some kind of connection. And then for me, it gets pretty tricky, because it seems like transduction is supposed to do that kind of work. And I'm just kind of at a loss. Okay, what does that mean? Like, what does it mean to think that relation that's sort of those two, the wave and the particle? So I'm not really sure where to take that at that point. I seem to understand how to think the sides in isolation, but then how do we think of that relation? That seems to be the question.
Yeah, I think in some ways that's sort of the central question of this whole the whole book, and in particular this whole part of the book, is how to think that relation. And I'm not sure there's a way to sort of sum it up in one sort of definition or one thesis or something like that. I think part of the reason why we go through some of these detailed scientific examples is he wants to sort of exercise us in the mode of thinking, so that we learn to think transductively, like in the process of doing so, by working through these examples, rather than having a transductive thinking be something like something that is set out in a thesis or something like that. But maybe more sort of specifically, we'll see in the next few weeks as we get to that double solution theory that I keep mentioning. So in the double solution theory, there's the relationship between the wave and the particle is much more, I guess, intimate, you could say, than in the standards theory. So it's not just that we have these sort of two complementary aspects or the two complementary concepts of the wave and the particle, but in this theory, the particle itself is a singularity of the wave, so that there's a real physical wave, not just a probability wave, and the particle is a singular region in that wave. So there's a sort of joint of those two sides of the continuous and the discontinuous in the actual physical representation of the theory. But we'll see more detail of how that works in the next couple readings. Okay, so let's go on to the next subsection, if someone else would like to read.
Subsection 2, quantum theory, notion of the elementary physical operation that integrates the complementary aspects of the continuous and the discontinuous. We will begin by attempting to express to what extent the adoption of a quantum principle modifies this conception of corpuscular individuation and extends the conversion of the notion of the individual initiated in relativist thought. Even if there is actually no rigorous epistemological interiority of one of the conceptions over the other in terms of physical theories, a logical interiority for the conception of individuation reveals itself. Indeed, the individual can be conceived as having a variable mass according to its relation with the other elements of the system in which it is included. To conceive these variations as continuous or discontinuous constitutes a supplementary specification contributed to the theory of relativity. However, this point of view is still too formal. The discontinuous quantification of possible degrees of mass and levels of energy indeed contributes a new type of relation between the same type of individuals. Due to quantification, a new condition of stability is brought into change itself. The existence of successive levels that correspond to increasingly large quantities for the corpuscle is the veritable synthesis of continuity and discontinuity. Furthermore, here we are presented with the possibility of distinguishing at a given time among individuals that belong to a system due to the actual differences of the quantum states that exist between them, which is something that Pauli's principle contributes to, and which is the key to a new logic of the individual. Pauli, I'm not sure, principle states, quote, electrons postulated as identical to the point that they could no longer be distinguishable in a system, however, cannot have in an atom or gas their four quantum numbers be respectively equal. In other words, when an electron is in one of these quadruply quantified states, this excludes for every other electron the possibility of being in the same state, whence its name as the principle of exclusion. In some sense, when it is completed by such a principle, quantum theory recreates a principle of individuation and stability of discernible states. The theory of relativity would lose by destroying the unchangeable substantiality of mass, which is a classical foundation for the identity of beings in a corpuscular theory. A new path for grasping the reality of the individual opens up with quantum theory, whose power of transductivity is so great that it allows for the establishment of a viable relation between an inductive physics of the discontinuous and a deductive energetic theory of the continuous. Planck introduced the idea of the quantum of action in 1900 due to his work on blackbody radiation, i.e. radiation emitted from the surface of a body that perfectly absorbs light when it is maintained at a certain temperature. Blackbody radiation can be decomposed by a classical type of analysis following Fourier into a sum of monochromatic radiations. If we want to know the energy that corresponds to an interval of frequency, nu, arrow, nu plus delta nu, In black body radiation, we must determine the spectral density or function rho of nu comma t, such that rho of nu comma t times delta nu gives the quantity of energy that is contained in the whole unit, contained in the unit of volume that corresponds to the spectral interval delta nu, if T designates the temperature of the surfaces of an enclosed chamber whose surfaces, including all the materials that it can contain, are maintained at a certain uniform absolute temperature. Here we are at the point of the encounter between an energetic theory, thermodynamics, and a structural research. Indeed, the theory of thermodynamics is what allowed Kirchhoff to show that this thermal equilibrium radiation in no way depends on the nature of the walls of the chamber or of the bodies included there, but only on a temperature T. Other thermodynamic understandings allow us to demonstrate that the quantity of energy contained in the unit of volume of blackbody radiation must increase by 4 powers to that of the absolute temperature T. This experimentally verified law is called Stefan's law. Ultimately, thermodynamics is what allowed Wien to demonstrate that rho of, I think that should be nu, T equals nu to the third times F over, maybe it is V, V over T, where F is a function of the variable V over T, which the thermodynamic approach is unable to determine.
Yeah, we can stop there. I'm pretty sure the last bit, it should still be nu, not V. I think that's a typo. They look almost the same, so it's hard to tell. But looking at the French, it's a nu, and that makes more sense in terms of the equation. So here, I think, again, some of the details of the physics are not super important. The basic principle that is important is that as a result of this research into blackbody radiation, Planck comes up with this idea or introduces this idea of the quantum of action. So the idea that there's a discrete set of energy states of the system that only that there's no intermediate states between these discrete energy states, and so now we have Planck's constant, which is represented with an H, we so there's a constant that appears in a number of different physical laws that has to do with the discreteness of the action, and we'll see a little bit more on this in the next couple paragraphs. Yeah, and that bit on the ultraviolet catastrophe we'll see in just a couple more paragraphs on what that has to do with the discreteness of action. So here we have, so Simondon characterizes this introduction of the quantum of action as unification of a continuous and a discrete theory, because it has to do with the wave theory of light and radiation in general, but it also is connected to thermodynamics, which is a theory of the discrete. It has to do with the motion of particles. So the introduction of this notion of a quantum of action sort of bridges between these two domains of physics.
Yeah, my understanding of the Stefan Boltzmann thing is that if you increase the temperature of this theoretical, hypothetical black body that would perfectly absorb all radiation, that increases the intensity of the light that it emits, and then the relationship between the wavelength of the light at the peak of its intensity is also dependent in a measurable way on the temperature of the object that's emitting it, which is apparently how you determine stuff like the surface or the temperature at the surface of the sun. It's by using, that's Wien's law.
Right. Thanks. Yeah, that helps. Yeah, and so it's as Angus just mentioned, this black body radiation is hypothetical or theoretical in the sense that there's no substance that is perfectly absorbent of radiation, but it has these consequences for actual physical observation as well that we'll see a little bit more in the next couple paragraphs. So I'll read the next bit, the next page or so. Where are we? Right. Thus, thermodynamic research here gave the indication of its own limits and invited scientific thought to go further through an analysis of the energetic relations between matter and radiation within the confines of an enclosure at determinate temperature. This was indeed a necessary encounter between the theory of corpuscles and the theory of electromagnetic radiation defined by Maxwell, between the culmination of research related to the theory of the discontinuous and that of researches related to the theory of the continuous. Here is how Louis Debray, in the cited work, presents the epistemological situation at this moment. Besides, this analysis seemed quite easy, for the theory of electrons then provided a very well-defined schema for the phenomena of the emission and absorption of radiation by matter. It was sufficient to suppose that the sides of the enclosure contained electrons in order to study how these electrons absorbed, on the one hand, a part of the energy of the surrounding black radiation, and gave back to it, on the other hand, a certain quantity of energy through the processes of radiation, and then to ultimately explain that the processes of absorption and emission statistically compensated one another in such a way that the spectral composition of the radiation at equilibrium remained at a constant average. Lord Rayleigh and Planck made the initial calculation, which was later confirmed by Jeans and Henri Poincaré. It necessarily led to the following conclusion. The function rho nu t must be expressed rho nu t equals 8 pi k over c cubed by v squared t, where k is a certain constant that intervenes in the statistical theories of physics and whose numerical value is well known. This is the Boltzmann constant, which is k equals 1.37 by 10 to the minus 16 in units of c. This theoretical law, which is known as the Rayleigh-Jeans law, shows an increase of rho as a function of nu, represented by a parabola that increases indefinitely without a maximum. This law leads to the conclusion that the total energy of black radiation would be infinite. This law is only in agreement with experiments for small values of nu for a given temperature. These experiments allow us to trace a bell curve representing the variations of rho according to nu for a given temperature. In terms of this new curve, the total quantity of energy, the integral should be 0 and infinity, rho nu t delta nu contained in the black radiation has a finite value that is given by the area included between the x-axis and the bell curve, according to the following empirical formula introduced by Dean. Rho nu t equals a nu cubed e to the power of minus bv over t. And so you can see the diagram there of the difference between the two formulas. The theoretical justification for Wien's formula remained to be discovered. Classical corpuscular theory is articulated by classical energetic theory in the following manner, marking a privilege of continuity over discontinuity. An electron animated by a periodic movement of frequency nu can continuously emit and absorb the electromagnetic radiation of frequency nu. However, this conception would be valid if it were supposed that the relation which constitutes the energy exchange between the corpuscle and the electromagnetic wave remained independent of the corpuscular individual. But if relation is conceived as having the value of being, then it seems to extend the wave's energy into the states of the corpuscle and to translate the corpuscle's individual reality into the wave's levels of energy. The fact that this relation is asymmetrical, i.e. creates a rapport between an electromagnetic field, thinkable according to the continuous, and a corpuscle, thinkable according to the discontinuous, necessarily requires relation to simultaneously express discontinuity in energetic terms and continuity in structural terms. Under this condition, it is not a simple rapport, but a relation that has the value of being. The quantum characteristic of relation defines a mode of reality that is different from structure and continuous energy, This characteristic is that of operation, which integrates within it the complementary characteristics of the continuous and the discontinuous. The characteristic of continuity in the operation becomes an order of quantum states which are able to be hierarchized in an increasing series starting from an absolute inferior quantity. The characteristic of structuration and individual consistency in the operation becomes the complementary aspect of this hierarchy, i.e. the characteristic of the quantification of exchange. Operation appears as a real relation or real mutual transduction between a continuous term and a discontinuous term, between a structure and an energy. So I'll go back to that diagram, which I've posted in the chat as well. And again, for whatever reason, the diagrams are not translated. They're just copied over from the French book. But I mean, it should be relatively straightforward for this one. So what happened, the development of the theory of black body radiation, we have this Rayleigh-Jeans law, which is developed theoretically from the idea of the equilibrium conditions in the black body chamber. So in the chamber within which a black body is emitting radiation. But this formula increases, it has a continual increase, as we can see in the diagram there, the little dotted line. So the higher the temperature, the greater the energy, and the higher the temperature and the frequency, the greater the energy that would be emitted by the black body, and it will just keep increasing forever. There's no limit to that increase. But then in actual empirical experiments with not true black bodies, but something approaching a black body, you end up, instead of having this indefinite increase, you have this bell curve type shape where the energy increases for a certain portion of the spectrum, but then it sort of levels off and then decreases again later on. And so just empirically, you can derive this formula, which has these two empirical parameters, A and B, which are just sort of set empirically. And then with that empirical formula, you can find that the integral, so the area of the region underneath the curve is finite. So there's, instead of having an infinite energy, you have a finite energy. So there's this disjunction between the theoretical accounts of how black body radiation should work and the empirical results. The introduction of the notion of the quantum of action is a way of resolving this this discontinuity or this disjunction between the two representations. Yeah, and then so as I think it's mentioned in the chat, the consequence of this notion of a quantum of energy is that the energy state of a system is always an integer times Planck's constant. So there's always you can have energy state of equal to Planck's constant, or 2 times Planck constant, or 3 times, etc. But you can't have 3.5 times or 4.72 times or whatever. It's there's a jump from 3 to 4 or 10 to 11 or whatever times Planck's constant. So it's not possible to have any intermediate states. Okay, so we can go on to the next bit if someone else would like to read, and you'll get some nice equations to read as well. Yeah, I can read again. No one else seems to be interested in reading these equations, so I'll read the next page or so. A substantialistic theory of the particle led to a continuous representation of the energetic exchanges between radiation and the particle. Planck supposed, on the contrary, that it was necessary to admit that an electron animated by a periodic movement of frequency nu can only emit or absorb radiation in finite quantities of value h nu, where h is a constant. According to this hypothesis, the function rho nu t must have the form rho nu t equals 8hv cubed over c cubed by 1 over e to the power of hv over kt minus 1. So you can take a look on the stream what exactly that equation looks like. With k always being the same constant as in Rayleigh's law, and h being the newly introduced constant. For small values of nu over t, Planck's equation is conflated with Rayleigh's equation, whereas for large quantities of this quotient, it leads to Wien's empirical formula. This formula is also in agreement with the laws of thermodynamics, since it gives for the radiation's total energy a finite quantity proportional to t, just as Stefan's law desires. And this quantity is that of the formula rho nu t equals nu prime f by nu over t, just as Wien's law requires. The constant h, Planck's constant, has the dimensions of the product of an energy by time, or rather of a quantity of movement by a length. It therefore has the dimensions of the physical quantity called action in mechanics. It plays the role of a unit of action. The constant h plays the role of a sort of unit of action, the role, it could be said, of an atom of action. Planck has shown through considerations which I will not develop, that this is indeed the profound meaning of the h constant, whence the name of the quantum of action that he has attributed to it. Here we see the intervention of an important element valid both for the history of ideas as well as for the research of the physical individual being itself. The introduction of the quantum of action into physics was indeed considered by Louis de Broglie in 1923 to 1924 as needing to be incorporated into the fusion of the notions of waves and corpuscles that he brought about within the framework of the classical conceptions on spatial-temporal representations and causality. This conception, which Louis de Broglie called the theory of the double solution, was described in the May 1927 issue of the Journal de Physique. Furthermore, alongside the normally envisioned continuous solutions of the equations of wave mechanics that were considered as having a statistical signification, this theory envisions other solutions that involve a singularity and that allow us to define in space the position of a corpuscle, which then takes on a much better defined individual sense due to this very singularity. The sense of these solutions is no longer statistical like the first ones. Counter to this theory stood the likes of Born, Bohr, Heisenberg, Pauli, and Dirac, who rejected the determinism of classical physics and proposed a purely probabilistic interpretation of wave physics, wherein the laws of probability had a primary characteristic and did not result from a hidden determinism. These authors dedicated themselves to the discovery of the uncertainty relations proposed by Heisenberg and to Bohr's ideas concerning complementarity. In October 1927, the Solvay Conference of Physics marked the conflict between deterministic and indeterministic representations. Here, Louis de Broglie exposited his doctrine in the form, which he qualified in 1953 as softened, of the pilot wave. At that time, he said, facing the almost unanimous disapproval attributed to my exposition, I had become discouraged and had returned to the probabilistic interpretation of Born, Bohr, and Heisenberg, to which I have retained faithful for 25 years. Nevertheless, in 1953, Louis de Broglie questioned if this faithfulness were fully justified. Indeed, he observes that David Bohm, an American physicist, had taken back up his old ideas in the shortened and barely defensible form of the pilot wave. He also observes that J.P. Vigier pointed out a profound analogy between the theory of waves with singularities and Einstein's attempts to represent material particles as field singularities in the framework of general relativity. Material corpuscles as well as photons are represented as singularities within the spatial-temporal field with wave characteristics, the structure of which requires Planck's quantum of action. This is how Einstein's conception of particles and those proposed by Louis de Broglie could be joined in the theory of the double solution. The grandiose synthesis of quanta and relativity would be realized in this way. So there's a lot of history of physics stuff in this. Right, here we go. So we saw the problem was the disjunction between the theoretical account of blackbody radiation and the experimental observations, and then Planck introduces this notion of a quantum of action, this discrete quantity represented by the constant h, and he introduces the new equation, which sort of bridges the gap between the theoretical prediction and the empirical observations, and so this new equation accounts for the experimental observations, but it also explains the theoretical basis for those observations. And then Simondon passes now to what this introduction of the quantum of action means for physical theory. And so here's some of the history. He goes through it a little bit quickly, but it's relatively straightforward that he sets out here. So Louis de Broglie initially developed had this idea about the double solution theory. So in addition to the quantum the quantum states of a system would be represented by these two. The equation would have two solutions. So one is a purely probabilistic one, which is the one that is sort of retained in the standard formalism, and then the other solution would be a discontinuous, a nonlinear equation that would have this singularity, which represents the particle, and this would be a real physical wave. So it's not just a probability wave like the linear solution to the equation, which is the one represented in contemporary physics. It's a nonlinear solution, which is a real physical wave. So that was his first conception. But there are certain mathematical difficulties with developing that account because of the nonlinearity of the equation, and so he sort of developed a simplified version of the theory, which he called the pilot wave theory. So on this account, there would be a particle and then a physical wave that would sort of guide the particle through its evolution. So there was this conference, the Solvay conference in 1927, where basically all the leading physicists of the time got together in this town in Belgium and debated the different interpretations of quantum theory. And Louis de Broglie presented this pilot wave version of his theory, and then it was basically universally rejected. Everyone thought it didn't work, and I think it was von Neumann who gave an argument showing that it was actually impossible for something like this to work. A hidden variables theory, so a theory that would explain away the indeterminate, chance or probabilistic aspect of quantum physics. So that would give a deterministic theory underlying the probabilistic side of quantum physics. So von Neumann, if I'm not mistaken, gave this argument, which was intended to show that it was impossible to have a theory of this form, a theory that would give an underlying hidden determinate account for quantum physics. And so with this rejection of his theory, Louis de Broglie gives up on the pilot wave and the double solution approach and sticks with the standard interpretation, the probabilistic one, and for 30 years or so. And then David Bohm picks up the pilot wave theory again, sort of out of the dustbin of history, and he shows that this supposed refutation of this possibility of a hidden variables theory is actually not valid. So it is possible to develop a hidden variables theory. And so he does this in terms of this pilot wave version of the theory, but then Louis sees this and goes back to his double solution version rather than the pilot wave version, and he picks that up again, and he argues that this approach to quantum physics has a greater potential for the unification with relativity, because in both the double solution theory and in general relativity, particles are represented as singularities in terms of the fields. So that's sort of the expanded version of the history that Simondon develops in that one paragraph there. Yeah, Angus, your comment there about von Neumann is probably, or it's at least plausible. Like I've been seeing like in different domains of things that I've been reading over the past few weeks, like von Neumann's name coming up in so many different areas. I mean, even the sort of basic architecture of computers is known as the von Neumann hierarchy, or von Neumann architecture. So he was instrumental in developing the formalism of quantum mechanics as it exists now, and in the construction of computers, game theory, like so many domains of math and physics and computer science are like products of his work. It's pretty amazing.
Yeah, I heard, I don't know if it's real, but I read about this story where he was attending some lecture, and the professor presented some sort of like long unresolved or unsolved mathematical proof, and von Neumann like thought about it for like 5 minutes and then walked up to the board and solved it.
Yeah, I could definitely believe that. He's one of these people that like you. It's like scary how smart he was, and like the ability that he had to solve different problems and so on. He was also involved in the Manhattan Project, I think, but he wasn't one of the central people in it. But yeah, he's a very interesting person in the history of 20th century science.
So I watched a helpful video about the pilot wave theory that described it in terms of the double slit experiment, which is that experiment where they sort of emit electrons at this wall that has two gates or doors in it, and the electrons make these weird interference patterns when both of the doors are open, and then like a different kind of pattern when one of the doors is closed. But apparently the quantum understanding of it is that when the electron is presented with more than one option, it takes both of them, and then it exists in a kind of state of superposition with relation to itself, and then it interferes with itself in this state of superposition to create this strange pattern on the, whatever the metal plate or whatever it is in the back they're using to detect the impact of the electrons. But I guess that the pilot wave theory, as you were saying, Nan, is a deterministic theory. So, each electron follows a determinate path, and it explains the behavior without resorting to superposition. But it does so by positing that the starting position of the electrons is indeterminate, which, as I understand it, is the hidden variable in the pilot wave, the pilot wave theory. I'll post that video link. It was pretty accessible.
Yeah, thanks for that. Yeah, so to expand a little bit on the double slit experiment, so what happens? So you have with light beams or beams of electrons, or you can even use beams of like molecules composed of many atoms. You can do this at a macroscopic scale, but you send a beam through this apparatus that has these two slits in it near each other, and you get this interference pattern on the wall behind the two slits. So if you shine a beam of light, for example, through these two slits, then you end up with a pattern of dark lines in the light that reaches the wall behind the two slits. But the weird thing that happens is that even if you reduce the intensity to the point where it's just one photon or one electron or whatever passing through the apparatus, you still end up with this interference phenomenon. So it would seem like, or what you would expect is that when you have an intense light beam or a more intense light beam shining on the double slits, you have some photons pass through one slit and some photons pass through the other slit, and then the two beams of the two rays interfere with each other after they pass through the apparatus, and that's what produces the interference, the dark lines on the back of the wall. But then, if that were the case, then shining or having one photon or one electron pass through the shouldn't produce any interference effects because the photon or the electron has to pass through one slit or the other. That's sort of what we would expect on a classical interpretation. And so in the Copenhagen interpretation, the standard interpretation of quantum physics, there's no determinate fact about which slit the electron passes through. So there's this sort of probability wave, and then so it has say a 50% chance of passing through one slit and a 50% chance of passing through the other slit. And the two probability waves interfere with each other and produce that interference phenomenon on the wall. And so the electron has no determinate position until it interacts with, or the photon, whatever it is. It has no determinate position until it interacts with the wall at the back of the apparatus. So there's a lot that seems very weird about this interpretation, like even to physicists. Like it's this probability is not, so it's not just probability in the sense of our knowledge or ignorance of the true state of affairs. It's a sort of inherent probabilistic aspect of reality, so that there's no determinate state of there's no determinate path that the electron passes through, and then suddenly, once the interaction with the back wall happens, then the whole the wave function collapses, so that instead of having a probability distribution, it suddenly takes on one specific value when it interacts with the back wall. So there's all these sort of weird conceptual difficulties with the standard interpretation. And then, so under the pilot wave theory, I don't know the sort of the details of how it accounts for this, but there's an actual physical wave which passes through both slits in the experimental apparatus and produces the interference phenomenon, and the particle is guided by this wave. And so the particle actually does pass through one slit or the other, a determinate slit. But the wave that is governing the behavior of the particle is what produces the interference phenomenon. And so there's it's a deterministic theory rather than an indeterministic one, because there's a real the particle has a determinate physical path through space rather than this probabilistic distribution over many possible paths. So that's the pilot wave version of the theory, and the double solution theory is related but a little bit different, and we'll see more on it as we continue to read. And maybe one other point that I'll mention is that the price you have to pay to account for these to avoid some of these conceptual difficulties, the price you have to pay is that the pilot wave theory and the double solution theory are non-local, meaning that there's more, I guess a short way of putting it is that there's action at a distance is possible under this theory, so that in classical physics there's only action, or under relativistic physics even, action of one particle or one entity on another can only happen through within the light cone of the one particle. So if an event A happens in one region, its effects can only propagate at the speed of light at the maximum out of that region. But so there's Bell's theorem, which is related to non-locality, and basically what quantum physics predicts, and this has been experimentally verified, is that the effects, or whether it should be understood in causal terms is not clear, but if you have a pair of particles that are emitted in an entangled state, so that they're part of the same quantum system, then one particle will have one state and the other particle will have a different state. So whichever state the one particle has, the other particle has to have a different one. And under the standard interpretation of quantum mechanics, the Copenhagen interpretation, we have this superposition depiction of the states of the particle. So the particle has no determinate state until it's measured. But then that means that you measure, say, the one electron on Earth, and then someone else measures the other electron on Mars, and instantaneously the one measurement determines the other measurement. So it doesn't take whatever minutes of time for the light beam to pass from Earth to Mars. As soon as I measure the electron here on Earth, the other electron on Mars has a determinate state, which is the opposite of the one that the electron on Earth had. And so that's what non-locality means in the Copenhagen interpretation. But under the in the pilot wave interpretation, and also in the double solution interpretation, I'm not sure exactly how they interpret non-locality, but it means that effectively at the fundamental level of physical reality, there's no, or I guess at the fundamental level of physical reality, everything is sort of part of this one quantum system that is evolving together, and even though areas of space might be separated so that the speed of light, they're separated so that it would take a certain amount of time for a light beam from one region to pass to the other. They're still evolving in tandem with each other. They're still part of the same quantum system. And David Bohm actually, I don't know a lot about this, but he was interested in like Indian mysticism, and sort of connected his account of quantum physics with this idea of this sort of fundamental unity of the universe and things like that. So it's kind of weird stuff, but it shows you avoid some of the conceptual difficulties of the Copenhagen interpretation, but you have to sort of accept some pretty strong ideas about what the fundamental nature of physical reality is as well at the same time. Yeah, the David Bohm is someone that I've been meaning to look into more, but so I don't know a lot about what exactly his or how exactly he makes that connection between Indian mysticism and quantum physics, because there's a sort of I guess New Age kind of like pretty thin version of this sort of quantum mysticism that is pretty prevalent these days. Like if you just go on a bookstore and search quantum, you'll find all kinds of like New Age stuff. But I think Bohm was someone who obviously knew very well what quantum physics was and was very developed this new account of quantum physics, and so it's in his case it's not just the sort of thin New Age account of the connection between mysticism and quantum physics. There's more to it in his case, but as I said, I haven't really looked into that at all. Yeah, there was I never saw that movie, but the like basic premise is sort of that New Age idea that like quantum mechanics shows that science like can't discover the truth, and you need mystical engagement with reality in order to have this in order to know the reality or something like that, which is a pretty limited version of what we can learn from quantum physics, I think. But yeah, it's I think Bohm has more. There's more to it in Bohm than that, but I'm not sure exactly what it is.
Shall I read the next section? Cool. For the study of individuation in physics, this doctrine presents quite a particular interest, for it seems to indicate that the physical individual, the corpuscle, can be represented as associated with a field without which it would never exist, and that this field is not a pure expression of the probability for the corpuscle to be in a particular point at a particular instant, probability wave, but that the field is a veritable physical quantity associated with other quantities that characterize the corpuscle. The field, without absolutely belonging to the individual, would be centered around it and would therefore express a fundamental property of the individual, i.e., polarity, which would be there in its simplest form, because a field is precisely composed of polarized quantities that are generally representable by systems of vectors. According to this manner of seeing physical reality, the wave-corpuscle duality would not at all be the apprehension of two complementary facets of reality in the sense that Bohr gives this expression, but instead the apprehension of two realities equally and simultaneously given in the object. The wave would no longer necessarily be a continuous wave. This is how the singular atomicity of action, which is the foundation of the theory of quanta, would be understood. The fundamental problem that wave mechanics poses for a theory of the physical individual is in fact the following. In the wave-corpuscle complex, how is the wave linked to the corpuscle? Does this wave belong to the corpuscle in some way? For the wave-corpuscle duality is also a wave-corpuscle pair. If we begin with the study of waves, the quantum aspect of the emission or absorption of radiation also involves the idea that the energy of radiation during its propagation is concentrated into a quanta of h nu, is that it? Consequently, the radiant energy itself is concentrated into grains, and thus we arrive at a first manner of conceiving an association of the wave and the corpuscle when the corpuscle is nothing but a quantum. If radiation is quantified, the radiant energy is concentrated into grains in quanta of the value h nu. This conception is necessary to interpret not only the photoelectric effect and the Compton effect, but also the existence of a clear limit on the side of the large frequencies in the continuous spectrum of X-rays emitted by an anticathode submitted to a bombardment of electrons in the Crookes or Coolidge tube, which is what allows for the experimental calculation of the constant h. It provides a basis for the construction of a satisfying theory of the atom and of spectral lines, according to Rutherford's representation, to which Bohr has applied a theory of radiation derived from the theory of quanta. The quantified Rutherford-Bohr atom, then, had a continuous series of possible quantified states, the quantified state being a stable or stationary state of the electron. According to Bohr, in quantified states, the electron does not radiate. The emission of spectral lines then occurs due to the passage from one stationary state to another. However, this doctrine forces us to consider electrons as corpuscles that can only take certain quantified movements. Einstein proposed in 1905 the interpretation of the frequency threshold of the photoelectric effect and of the law that yields the kinetic energy of photoelectrons. T equals K times, is it nu, with the zero that is something else. Remedial math, folks. Where nu is the incident frequency and V nu 0, I don't know how you read that, the threshold frequency. After returning to the old corpuscular theory of light in a new form, by supposing in a monochromatic luminous wave of frequency nu that energy is rolled up in the form of a corpuscle of energy h nu, h being the Planck constant. Thus, according to this theory, there are grains of energy equal to h nu in radiation. The frequency threshold of the photoelectric effect is then given by the equation of the frequency threshold nu something something, and you guys can fix that for me in post, in which W here is the electron's work function.
Yeah, you were trying to avoid the equations, but you got a couple of them. Yeah, so it's the last equation is nu 0 equals W0 over H, and W0 is the electron's work function. And so that this is related to the photoelectric effect that we discussed, I think, 2 weeks ago. So this is the work function is the amount of energy needed for an electron to be emitted from the piece of metal that's being illuminated by a ray of light. And so Einstein proposed this discontinuous interpretation of the photoelectric effect. So yeah, there's a few different phenomena that in the beginning of the 20th century, around 1905, they all get reinterpreted or explained through the notion of this idea of the quantum of action and Planck's constant. And so that's sort of the big picture of what is going on in that last couple paragraphs. And then, sorry, that's the last paragraph, and then the previous one. So he's pointing to the idea that in this double solution theory, the relationship between wave and corpuscle is not it's not one of complementarity. That would be sort of a conceptual relationship or a conceptual disjunction between them, but the wave and the particle are real physical entities or aspects of reality that interact with each other in a physical manner. So that we need a physical account of how the wave and the particle interact with each other. And so it overcomes this complementarity conception where we have these sort of two incompatible concepts that are supposed to represent different aspects of reality. Okay, so let's go on to the next bit I can read. We're almost at time, so this might be our last reading. Okay. The K constant of the experimental law cited above must be equal to the Planck constant, since the electron will escape with a kinetic energy equal to T equals h nu minus W0 equals h by nu minus nu 0. An equality that verifies that experimental study of visible light, X-rays, and gamma rays, as revealed particularly by Millikan's experiments, with a surface of lithium and then a sodium receiving the light emitted by a mercury arc valve. The experiments of Maurice de Broglie for X-rays, and finally the experiments of Thibault and Ellis for gamma rays. In the theory of photons, the photon's individuality is not purely that of a corpuscle, for its energy, given by the expression E equals h nu, requires a frequency nu, and every frequency presupposes the existence of a periodicity that is not at all implicated in the definition of a corpuscle, consisting in a certain quantity of matter enclosed in its spatial limits. The photon's quantity of movement is guided in the direction of their propagation and is equal to h nu over c. Relative to the upper limit of the continuous spectrum of X-rays emitted by an anticathode, the Duane-Hunt law measures this maximum frequency by the expression nu m equals T over H equals ED over H. However, this law can be interpreted directly by admitting that after the slowing down of the electron incident on the matter of the anticathode, X-rays are emitted by the photons. The largest frequency that can be emitted is the one that corresponds with the case where an electron loses the totality of its kinetic energy in a single stroke, T equals EV, and the maximum frequency of the spectrum is given by Vm equals T over H equals EV over H in conformance with the Duane-Hunt law. Ultimately, the theory of the photon was corroborated by the discovery of the Raman effect and the Compton effect. In 1928, Raman showed that illuminating a substance like benzene with a visible monochromatic radiation of frequency nu yields a diffused light that contains, beyond the frequency nu itself, other frequencies of the form nu minus nu ik, where nu ik are infrared frequencies that can be emitted by the molecules of the diffusing bodies, as well as frequencies in the form of nu plus nu ik with a much lower intensity. The explanation is clear concerning the theory of photons. If the molecules of the diffusing body are capable of emitting a radiation of frequency nu ik equals minus EI minus EK over H, because they're capable of two quantified states of energy, EI and EK, which is less than EI, the body illuminated by the photons of energy H nu will emit diffuse photons after the encounter between the photons and the molecules. The exchange of energy between the molecule and the photon of energy H nu will be translated by an increase in frequency if the photon has gained energy, and by a decrease if it has lost energy. If a molecule gives to a photon the energy EI minus EK by passing from the quantified state EI to the quantified state EK, the energy of the photon after the encounter will be H nu plus EI minus EK equals H by nu plus nu ik. In the inverse case, the diffuse photon's energy will be H nu minus EI minus EK equals H by nu minus nu ik. In the first case, the photon's frequency will be nu plus nu ik. In the second case, it will be nu minus nu ik. So again, some of the details of the physical experiment. Some of the details of the physical experiments are not that important here again, but this is basically just showing a number of different areas where this introduction of the notion of a quantum of action explains these effects that were not explainable under the previous account under the continuous interpretation. So that's sort of the big picture, but some of the details are not super important, I don't think. So I think maybe it would be a good idea to stop here for now. I think we're all a little bit worn out by some of the physics that we've been going through. So we can stop here and pick up with the Compton effect next week. And we'll see more about the double solution theory and why Simondo thinks that that's the better account of quantum physics. Okay, so thank you everyone for your questions and contributions, and hopefully see you all next week.